So this is the last module with new content of the entire CpE 100 course. So in this module, module 24, we're going to talk about the timing of sequential circuits. So how fast can we run these circuits? Right, when we buy a processor, we think, oh, I want to get the fastest processor as possible so that I can, do my work as fast as possible. So we'll talk about the flip-flop timing constraints, both the input and output timing constraints. The input constraints are the setup and hold time, and the output constraints are the propagation and contamination. So propagation and contamination clock to Q times. So we'll introduce and talk about those. And then we'll talk about, well, how fast can we run that clock? What is the cycle time of that clock? And that will be determined by the setup time constraint, also called the cycle time constraint. And whether or not it can run reliably is determined by the hold time constraint. So this analysis of both setup time and hold time, that consists of timing analysis. And so we'll end this module with a timing analysis example. So we've talked about flip-flops, D flip-flops, and they sample D at the rising clock edge. So that means that D has to be stable when it's sampled. So for example, if we're sampling D, here's D. Again, this is a timing waveform with time in the x-axis. So if we're trying to sample D and it's transitioning, instead of getting 1 or 0, we sample some intermediate value. And like we talked about with static discipline, that may not be a valid 1 or a 0. It may be in that forbidden zone. And so we want to make sure that we sample D when it's stable, either 1 or 0, but not transitioning. So this is similar to a photo. We want that thing that we're sampling or we're taking a picture of, we want that to be stable. So you can think of where someone runs across your photo and now you just get this blurred photo, which is kind of garbage. You'd wish they'd either stayed where they were or moved to their end location before or after you took the picture. So you wanted it to be a stable signal, not one that's changing or in our photo picture moving. Okay, so let's talk about how we can make sure that D is stable. So we look at our clock. So here's our rising edge of our clock. And we want to make sure that D, here's D, we want it to be stable. We want it to be either 1 or 0. Doesn't matter which one of those it is. We want it to be 1 or 0 at the sample time, so at the clock edge. But actually we want it to be stable around the clock edge too. So these hash lines mean that D can change. So D can change, transition, high to low, low to high, whatever. Outside of the sampling time, this setup and hold time. So setup is the time before the clock edge where D has to be stable. And the hold time is the time after the clock edge. The data must be stable. And this time together we call the aperture time. Setup plus hold. This is similar to in old cameras where we have the aperture opening up to expose the film, and then we get our picture and close the aperture again. Okay, so where do these numbers come from? Well, let's think about our flip-flop. Well, this picture doesn't really cut it. I can't just look at it at that level. It doesn't really give me any information. If you remember, our D flip-flop consists of 2 back-to-back latches. And so we have D coming in, Q going out, and we have some internal node N1. We have clock going into one of those latches, the rightmost latch, and clock bar going into the left latch. So if we think about it, when clock is 0, well, D is able to pass through to N1. That takes some time. So that time it takes for a stable D to get to the internal node, that's the setup time. So time before the clock edge, but we're actually sampling is N1 at the clock edge, not D. D has to actually travel or propagate through to N1, and that's actually what we're sampling. So this setup time is essentially the propagation delay through this first latch. Now let's look at the hold time. So the hold time is the time after the clock edge where D can't change. So, well, why does it matter if D doesn't, changes after the clock edge? So here's our clock going high. We say for some time afterwards, we better keep D stable, either high or low. Why is that? Well, if we look at this, the clock is transitioning from 0 to 1. The clock bar is transitioning from 1 to 0. Okay, so when it's 1, D is being allowed through to N1. You'll notice the clock goes from 0 to 1, but remember there's this inverter delay here to get the transition down to 0, so to cut off this latch L1. So that hold time is essentially the time it takes to shut down L1 after the rising clock edge. So then we back up a level of abstraction and talk about it again at these abstract levels, but now we've dived down into the details of where those numbers actually come from, and we see that, well, there's some time, again, before the clock edge that D has to be stable. Well, it has to get through L1 to that internal node before the clock edge. That's our setup time. And then has to be stable after the clock edge for some time T hold. And that's the time it takes to get the leftmost latch L1 shut off, so it's opaque. Again, remember those two times together are called the aperture time. Okay, so those are the input timing constraints. So D, the input, what the constraints are, the timing constraints are for that input. Now we can look at the output timing constraints. So when, after the clock edge, do we get the output Q to change and be stable? So if we look at our, again, we'll dive down a level up of abstraction and get to our back-to-back latches drawing of our flip-flop. So L1 and L2. We have clock coming into L2 and clock bar going into L1. And so we get a clock edge. Clock goes from 0 to 1. It actually takes some time for N1 to propagate out through to Q and change Q. So that time is the propagation and the contamination delay. Remember, we can have a minimum delay, contamination, and a maximum delay, propagation. The output Q could start to change as early as T, contamination clock to Q, but it's guaranteed to be stable after a propagation clock to Q. So we have this extra TPCQ. CQ means from the clock edge, because that's what's driving this change, is the clock rising from 0 to 1. So clock to Q means, so CQ means clock to Q changing. So we basically have a maximum delay. It's a propagation delay. The output is Q is guaranteed to be stable, and a minimum delay. Could start changing as early as TCCQ after the clock edge. So now let's talk about dynamic discipline. We've talked about static discipline, where we're just worried about ones and zeros and noise margins. So the static value of 1 and 0, how can we determine or make sure that those will have noise margins and be able to deliver valid ones and zeros? Dynamic discipline is making sure that our timing constraints are met. So we have two constraints, setup time constraint and hold time constraint. let's talk about both of those. And we'll use the flip-flops input and output timing to determine what these constraints are. So overall, this dynamic discipline says that synchronous sequential circuits, the inputs must be stable during the aperture time. Okay, we already talked about that. Specifically, they have to be stable at least a T setup, a setup time before the clock edge, and a hold time after the clock edge. Okay, so let's take a look at this. Here's a picture of some register R1, some combinational logic, and another register R2. And we want to figure out the delays of this circuit. So one thing we can do is if we get a clock edge here, we get a rising clock edge, it'll start driving data out through the register, through the combinational logic. It'll be stable by the next clock edge. So we can sample it out of R2, register 2. So this time, remember, it's called the clock period or the cycle time. So our clock is going high, low, high, low, high, low, blah, blah. So here's our clock. And the period, so when it repeats, this is called the clock period or the cycle time. And we'll use the term TC for that, cycle time. Okay, well, when can we get this next clock edge? Here. When we get one clock edge, it starts to drive it out of the flip-flop. Well, how long does that take? The maximum time is propagation clock to Q, to get out of the flip-flop and to change Q1. And then from last time, from chapter 2, we know that the longest delay through the combinational logic is called TPD. It's guaranteed to get to D2 and be stable at propagation delay later after it arrives here. Okay, and then we said, well, it really takes some time to get into that internal node, N1 here, and that time is the setup time before the next clock edge. So only after propagation clock to Q plus propagation delay plus setup time can we actually get that next clock edge, rising clock edge. For the cycle time, TC has to be greater than or equal to, well, propagation clock to Q, get out of the register, R1, plus TPD, get through the combinational logic, plus T setup, get into the internal node. We can also rewrite this in terms of TPD because this is the part we have control over as a designer, the propagation delay of the combinational logic. We can redesign that combinational logic to make it have a shorter path. So we can take everything else to the other side of the equation, and we get TPD has to be less than or equal to TC minus TPCQ plus T setup. And ideally, right, we'd use the entire cycle time to do useful stuff, to do our calculations in our combinational logic. But we have this overhead to get it out of the register and into the next register. And this is called the sequencing overhead. It's basically the price we pay out of our useful time, our cycle time, to do sequential logic. So we also have the hold time constraint. So that is that D2, so we get a clock edge. This is the same clock edge for both of these, right? These both have clock coming into R1 and R2. We get the same clock edge. We want to make sure that data doesn't race through. Well, the fastest it could get there is contamination clock to Q, out to Q1. And then TCD is the fastest it could get to D2. We want to make sure it doesn't start changing D2 here until a hold time after the clock edge. So basically this path can't be too fast. I want to make sure that TCCQ, the fastest it could get out of the register, plus TCD, the fastest it could get through the combinational logic. We want to make sure that that is greater than the hold time. Otherwise, if it's smaller than that, it could start changing D2 here, for example, before that hold time constraint is met. So in other words, before L1 is completely opaque or turned off. And so we can also write this the other way. T hold is less than TCCQ plus TCD. Again, as designers, as logic designers, this TCD, that short path, is what we have control over. So we can bring this to the other side and say TCD has to be greater than T hold minus TCCQ. In this picture, the hold time constraint is met. So the clock edge arrives, the data fastest it gets out of the flip-flop to change to Q1 is TCCQ, and then the fastest that signal goes through combinational logic is TCD, and that was greater than the hold time after that clock edge. So it started to change here, started to change D2 here, no problem. That was after the hold time. D2 couldn't start changing here, that would have been a problem. If it had raced through and started to change as early as, this red line I've drawn here. So that would be a violation as drawn. This hold time constraint is met. TCCQ plus TCD is in fact greater than T hold. Okay, so let's do these two analyses. It always consists of both of these. Always have to do the setup time constraint and the hold time constraint to do timing analysis. So let's do an example here. We have some characteristics of our flip-flop, our registers, and some combinational logic timing constraints, propagation and contamination delay for each of the gates. So let's figure out what the combinational logic constraints are, propagation delay and contamination delay. Well, propagation delay, the longest path, critical path, is from A or B to Y prime. So that's 3 gate delays. So 3 times T PD gate equals 3 times 35 picoseconds, 105 picoseconds. And TCD, well, where's the fastest path here? From D to Y prime is fast, and also from C to X prime. So that's a single gate delay. We make sure we use the contamination delay. We want the fastest it could get from an input, in this case C or D, to an output. So this is a single contamination delay of a gate. So that's 25 picoseconds. Okay, and now we can use what we just derived. The cycle time is going to be equal to, well, propagation clock to Q, get it out of the registers. How long does that take? So that second latch, basically, L2, plus TPD. Well, this is the worst case that we're going to have all of our signals, X prime and Y prime, stable. And then the time it takes after that worst case time to get into the next set of registers, the setup time. Okay, so we put our numbers in there and we get TPCQ is 50 plus TPD that we just calculated, 105, plus setup time is 60, all those in picoseconds. Our cycle time is, add those all together, we get 215 picoseconds. What's the relationship between frequency and clock period or cycle time? Well, it's a 1/over relationship. So the frequency is 1 over 215 picoseconds. It ends up being about 4.7 gigahertz. Okay, now let's look at the hold time constraint. Was this short path long enough? Right? So if it's too fast, then we have a problem. So TCCQ, that was 30 picoseconds, plus TCD of the logic, 25 picoseconds. Is that greater than the hold time? So the hold time is 70 picoseconds. And we see, oh, nope, that didn't work. 55 picoseconds is in fact not greater than 70 picoseconds. So our hold time constraint was not met. So that means that this circuit will be unreliable at any frequency. I can't just increase the frequency to fix this. If I made some mistake in my frequency calculation or my clock period calculation, I could say, oh, whoops, let's just make that bigger. I had a larger TPD, for example, than I calculated. No problem. After I've made the chip, I can go and increase the cycle time. We're all good. This one, we cannot fix after the fact. If there's a hold time constraint, these chips have to be just thrown away. Okay, so this hold time constraint wasn't met. What do we do? Well, we basically need to slow down that signal so it doesn't get a clock edge, race over to here, and start changing things before this register or these flip-flops aren't sampling that signal. Basically shut off that L1, that left D-latch. So, well, we can add a buffer here. That's fine. That was one of the TCD, the fast paths. And here's another one. So we have to make sure we change all of them. Did it change our critical path? No, turns out it didn't. So it actually didn't increase our cycle time at all. But now we have TCD. Instead of 25 picoseconds, we have 2 gates for the short path. So 2 times. We still use contamination delay, though. I'm going to use the fastest path. And we get 50 picoseconds. So now we get 30 plus 50 picoseconds. Is that greater than 70 picoseconds? Yep, 80 is bigger than 70.